empirical rule, plus or minus 1, 68%, plus or minus 2. We found your z-scores because we said you can find other ones besides 1 away from the mean, 2 away from the mean, 3 away from the mean. And we call that your standard z-score. What I want to just look at for a second is, here's your standard curve. You get a mean, you get a standard deviation. And we looked at these before. So let's say, for instance, your mean was 40 and your standard deviation was 5. This is what we did before, 40. Then we came to the 1 and we said that'd be 45. Then we came to the 2, that'd be 50. We came to the 3, 55. Right? We're doing this. You do this in Algebra 1. We did this in the beginning, back in Chapter 2. We kind of took a break from it, but now after you do your probabilities tie into your z-scores. The total area under this curve is 1. What's the total sum of all your probabilities? 1. So the area under this curve is going to tie into what we did for probabilities. And we're going to find the probability of something happening. The probability of getting a score of 45, or less than 45, greater than 45, between 30 and 45. We're going to find our probabilities because your area under your curve sums up to 1. Now, your z-score are these guys. Your z-score, and if you can write this down somewhere, it's called a standard score. It tells us how far away, how many standard deviations a value of x is from the mean. Okay, a z-score is a standard score which tells us how many standard deviations a value of x is from that mean. So for instance, an x value of 45 has a standard score of what? 1, because it is 1 standard deviation above the mean, right? An x value of 30 has a standard z-score of what? -2, because it is 2 standard deviations below the mean, right? A z-score, an x-score of 41, not on my chart, but we learned a formula, x minus the mean over the standard deviation. Remember when we did this back in Chapter 2? 41 is right here somewhere. So 41 minus 40 over 5 gives me my standard z-score of 1/5 or 0.2. So I am 0.2 standard deviations above the mean. We use that formula, x minus the mean over the standard deviation.
Oh, the standard deviation.
The standard deviation is 5. That standard deviation is not to be confused with your standard z-score. It has a mean, it has a standard deviation, but we find the z-score, the standard score, which tells us how many standard deviations it is to the left or to the right of the mean. A standard deviation itself cannot be negative. A z-score can be negative. I can fall below the mean. If I fall below the mean, my standard z-scores are negative. If I fall above the mean, my standard z-scores are positive. So if I said to you, I have a value of 32, is my standard z-score going to be negative or positive? Negative. If I have an x value of 40.5, is my standard z-score going to be positive or negative? Positive. These are the things I want you to see. And this is why I ask you to sketch these. So that's one of the reasons. And you probably say, yeah, that's so obvious. Well, I can tell you how many kids always give me positive z-scores because I think kids just like to subtract the bigger minus the smaller. Since you were little and in grade school, they always said the larger minus the smaller when you subtract. So I can't tell you how many kids subtract the larger minus the smaller and always give me a positive, even though it is negative. So I tend to dwell on this a little bit, and we do sketches. And I like you to use your mean and your standard deviation in the beginning so that we can see where they're falling. Once you get used to it, do you have to sketch? No, but that'll be a while before I tell you not to. Now, all your attributes of this, I put on your sheet for you. This is a normal distribution. A normal distribution has the mean, the median, the mode in the middle, all the ends in the middle. The total area of your curve adds up to 1. All your probabilities add up to 1. So we're going to see that this is going to tie in together. It's bell-shaped and it's symmetric about the mean. And we know that. We know that even from algebra 1, algebra 2. If this is 32%, this was 32%. 34%, this was 34%. Plus or minus 1 was about 68%. It's symmetric about the mean. And remember we did what was usual, what was unusual. Anything from here to here we considered okay, usual. Anything between -2 and 3 we considered unusual, and up here as well. We looked at this. Anything above 3 or below -3 we said is very unusual. In fact, in your book when we flipped it to a percent, we said anything below 5% was unusual because it's less than 5% of your curve that's left. That's where the unusual came from with the 5%. I said as soon as we came back to the normal curve, you would see it a little bit better. So anything that was down here, less than 5%, unusual. Okay? If you remember back to your empirical rule says plus or minus 1 is about 68%, plus or minus 2 is about 95%, plus or minus 3 is 99.7. It's almost your whole curve, almost. Another thing that we're going to see is all right. So this is good for here so far. We looked at this in chapter 2. This curve follows along here, never touches that axis. It gets closer and closer and closer. So you can technically have a z-score of -100. Your area to the left is virtually nothing. It's probably non-existent, but we'll say 0. So this never, it's like an asymptote. It will never touch that. And the same thing on the right-hand side. We always look at area under your curve as cumulative area from the left. It doesn't touch this axis, ever. It's like an asymptote. Your table, however, stops at 3.49 and stops at -3.49. Did you take a table? Okay. I thought maybe you want to keep that handy in your notes rather than look around in your book. So I thought I would just give you another one. Okay. So, also we have what we call an inflection point. An inflection point is at the plus or minus 1. It's technically where your curve was curving down, it changes its mind and starts to curve up. We see inflection points in pre-calc. And if you guys remember your inflection points, so it's halfway between, we considered in pre-calc halfway there. But in calculus, you have a whole another way to calculate an inflection point. We don't calculate any of them here. We just know that it happens at the plus or minus 1. We don't even use the concept of inflection point. The only time they do in this little unit is for you to estimate where the standard deviation is. And it's very difficult to estimate an inflection point if you don't have some kind of a formula, because not all your curves will look like this. Some of your curves, even though they're normal curves, will be a lot wider. And you have to kind of figure out your inflection points. So we just know that our inflection points happen at plus and minus 1 standard deviation. Okay? And we don't really use an inflection point for any other thing here. It is a concept we use in pre-calc and calculus. Okay, now, as we look at these, we did this before, back in chapter 2. We said your standard deviation measures how much something deviates from the mean. So if your data is closer to the mean, you have very small deviation, right? You have a small standard deviation. If your data is spread out, they vary and they differ a lot more from the mean, your standard deviation is greater. So if you take a look at this chart right over here, it's in your book as well. I might be a little bit off the way I moved that A, but this is in your book. Which of these curves, A or B, has the greatest mean? Look again. A. The mean is in the middle, isn't it? So which number would be greater? A would be greater. Which curve, A or B, has the greater standard deviation? B. Why? It's wider. Good. It varies a lot more than the mean, from the mean. Take a look at this graph. Which curve has the greatest mean? B. Follow your number line. Your mean is in the middle. Your mean is in the middle. So this guy's got about a 48, 49. This guy's got about a 61, 62, somewhere. Which curve, A, B, or C, has the smallest standard deviation? A. It's the narrowest. It varies the least from the mean. Which curve has the greatest standard deviation? C. Good. It's wider. Okay? That kind of we did before. Okay, I'm going to skip those because I don't like those. Now, we're going to go to your standard normal curve. Your standard normal curve is this special normal curve. You know how we put the mean and the standard deviation on the other one? Most of the time we'll use your normal curve. Sometimes we go to a standard one when we're just going to find, I'm going to give you a z-score, you're going to give me an area. We don't care what the mean is, we don't care what the standard deviation is. So we're going to set it at, okay, let's just start with that your mean is 0 and your standard deviation is 1. This is going to give you a standard normal curve. It has all the attributes of a normal curve. It's symmetric about the mean. It never touches the axis. It has the inflection points. The area still adds up to 1, but it has a couple of other attributes here. And if you kind of look at the paper that I gave you, it looks exactly the same as yours. It just says that it's going to go to negative 3.49 and positive 3.49. Actually, that's what your table goes to. Your calculator is far more exact when we put it in the calculator, but your table only goes to 3.49 and negative 3.49. Okay? This is important. The cumulative area for a z-score of 0, your standard score of 0, your area accumulates from the left. And didn't we see that with your percentiles? When we did percentiles, didn't we put percentiles from here to 100? When we were looking to see what percentile something fell in? Your area accumulates like you read, from left to right. So the area to the left of the z-score of 0 would be how much? In percent. How much of your curve is that? 50%. This is important because this is what's going to also help us when we eyeball this and figure out where our areas are. Your area to the right is also 50. Because your total area is 100% or 1. Okay? So therefore, what happens while your table ends up here, if I'm looking at a z-score of -4, there's essentially, you'll have to say 0 area to the left. It's like 0.0000 something. It's negligible. It never is exactly 0 because it doesn't touch the axis, but for our purposes, we'll say 0. When we do it on your calculator, you make it a little bit more exact because it's going to flip it to a scientific notation number. But we'll get to that part. Okay. So therefore, if we want to find the area under your curve to the left, okay, let me do this one. Find the cumulative area, its area to the left, that corresponds to a z-score of 1.15. Our mean is 0. Our standard deviation is 1. We have a z-score of 1.15. These are your standard z-scores right here. And I gave you a graph if you want to put it on there just so that you get the feel of where this is going. Please do, because this is really, really important, this part. So we're going to find 1.15. It's slightly to the right of 1. Now, we look at the cumulative area. Area accumulates from the left. When we look this up, we know it should be more than 50%, right? It should be pretty high. Because isn't it kind of unusual to be out here? You have a very, very small percent if you think about your plus or minus 1, your plus or minus 2. You have a really, really small percent out there. So it should be a good chunk of your curve. Now, of course, when we do this, when we write it ourselves and sketch it ourselves, we leave a little bit more room. Otherwise, we'd be squishing everything together. But that area out there is really, really small. So if you pick up your chart now, and we did this in chapter 2, so it might sound familiar. You go to your positive. Remember here, this is your hundredths position. This is the 5 right there. This part right here is located over here. So you're going to find your 1.1. You're going to find your hundredths position here. And you're going to pull up that area. You're going to take this number apart. We're going to put your 1 position and your 10th positions over here, 1.1. You're going to go to 0.05 because that's this number right there, the 5. And you're going to line it up like this and pull up this area right here. So what area do you find? What's the number? What's that decimal number that corresponds right there? Look at your chart, guys. Good. That tells me the area to the left of this is 0.8749. If I move my decimal place 2 places, it's covered 87.49% of my curve. 87.49% of my curve lies to the left of this z-score.
I was just going to say, like, why did you round that one down to something?
I didn't round anything. This number, if I broke this apart, would be 1.1 plus 0.05. So I want you to pull your 1s and your 10ths over here, and this part is your hundredths. Do you notice across the top, it goes 0.00, 0.01, 0.02? This is your hundredths position. This is your 1s and your 10ths. You have to pull your number apart. So you get your first 2 positions there. Okay, let's look up a score of a z-score of negative 0.24. Which side of the 0 does it come on, the left or the right? The left. And it's very close to the 0, isn't it? Negative 0.24. If I look up the area to the left, should it be greater than 50 or more than 50? I'm sorry, greater than 50 or less than 50? I confused you all, sorry. I confused those that were listening to me. It should be less than 50%, right? This is your benchmark. This is how you know you looked it up correctly. And in a little while, we're going to find area to the right, which means we have to subtract it from 1. So if you use your chart and you get this part of it, you will get the rest of this. So look this up. How do I look this up? On my negative side, what do I look up in my left-hand side? Negative 0.24. Nope. So negative 0.2. You're right, sorry. I thought you said 2.0. Negative 0.2. And look up the 0.04 and find me that area. Look at your negative side. Oh, be careful on the negatives that it goes backwards. It goes backwards. It goes from 9 to down to 1. 4090? So didn't we say it would be less than 50%? On the negative side. It's on the other side of your graph. Now, 4052? Okay, 4052. Okay. Now, tomorrow we're going to concentrate a little bit on what happens to the right, what happens in the middle, and we're going to look for symmetry.